Yes,
Hello?
sir.
Can you hear me?
Yes, sir.
Right. Okay. So, yes, in our last class, we have seen about the AC waveform, right? Which is something like this. Right? It could be either cos or sine. We would say if this one is V naught, we can write this as, right, this will be 2 pi V naught sine omega t, right, where omega equals 2 pi f, right, and f equals 1 by t, right. All these things you can extract from the waveform, right. So now let's see how your passive circuit components, which are resistor, capacitor, and inductor, right, inductor behaves when they are connected to a AC signal, right. Now first consider a resistor, right. So I'll draw the circuit something like this, right. So you have right or let this be V naught sine omega t, right, V naught sine omega t, and your question is to calculate the current I. Right, your question is to calculate the current I. So what is the current I? Right, you can apply Ohm's law here, right. So V equals I into R. What is your V here? V is this one, right. So I'll write this one, V naught sine omega t equals I into R, right. So simply I can write my I equals V naught divided by R into sine omega t. Clear? Sine omega t. See here the multiplier or the scaling factor, right? This indicates the sine wave with the function frequency of omega, angular frequency of omega, but the multiplier is divided by a factor r, right. So just consider if your r is greater than 1, then your waveform will be something like this. Am I right? And this magnification or this magnitude will be V naught divided by R, right? V naught divided by R. Can you see it clearly? Right? So look at here, there are no phase shift, right? This is sine omega t, and here also we have sine omega t, right? So the frequency and phase will not change when an AC current source is connected to a simple resistor, but the scaling factor will be reduced or increased, right? For example, if R is 0.1 ohm, this will be 10 V naught, right? That depends on the value of R, right? The scaling factor will be modified based on the magnitude of this resistance R. Clear, right? So the frequency or phase will not change. So I can simply say a resistor does not offer any phase shift to an AC signal, right? Now we'll move for the capacitor. Right, capacitor. Again, this is same E naught sine omega t, and then I have a parallel plate capacitor. Right, this will be E naught sine omega t. This is parallel plate capacitor with a capacitance C, right? With a capacitance C, right? So we can write the total charge stored in this capacitor Q equals C into V. Am I right? Capacitance into the voltage applied across the capacitor. Right, then simply differentiate this with respect to time, right? This be equation 1, differentiate equation 1 with respect to time. So I can write it as dq by dt equals C is a constant. Am I right? Capacitance of a capacitor is a constant. So C into, but B is a variable, or a variable with respect to time. So d dt of P. Right? What is dq by dt? What is dq by dt? Rate of flow of charge, which is your current I. Right? Current I. I equals C into d dt of V. Right? d dt of V. Now, what is your V? What is your V across the capacitor? Which is E naught sine omega t. Am I right? E naught sine omega t. Just apply that one here. So you can write this one as C into, again, E naught is a constant. Am I right? E naught into, right, d dt of sine omega t. Am I right? d dt of sine omega t. Right. Now, what is d dt of sine omega t? What is d dt of sine omega t?
Cos omega t into omega.
Yes, right, cos omega t into omega, right? So I can put my omega in front of this, right? So I can write it as C into omega into E naught into cos omega t, right? Cos omega t. Right, again, I can write my cos omega t into sine 90 plus theta. Am I right? Cos theta equals sine 90 plus theta. I can write this one as, right, omega c into E naught sine omega t plus pi by 2, right, which is 90. Pi by 2. Right, now look at here, your input is E naught sine omega t, right, but your output is this one. Compare these two, right? Compare your input and output. Right, when you are comparing your input, look at here, you had V naught by R, right? Resistance, right? So I can write this equation as, right, this omega c. What I can do is E naught by 1 over omega c. Am I right? 1 over omega c. Instead of multiplying it, I am dividing it by 1 over omega c, which will be omega c. Am I right? Right? These two are equivalent. And then I have a plus 90 degree here. Right? Sine omega t is there, which represents the sinusoidal wave here. But I have a plus 90, which is started before your input. Right? So I can write this 1 over omega, right? 1 over omega c as resistive equivalent of a capacitor, which is xc, right? That is equal to 1 over omega c, right? R and then xc, right? I can write xc as 1 over omega c. Okay, right. Here, look at this one. Your R does not depend on frequency f. Am I right? Or omega. Right? R is not depends on your frequency of the input waveform, but xc depends on your frequency. Am I right? Xc depends on your frequency. Right. If omega equals 0, what will happen? If omega equals 0, what will be your Xc? What will be your Xc?
Infinity.
Yes, that is infinity, right? So Xc equals infinity. Yes, yes.
Infinity.
Yes, right? So at steady state, right? What does means if omega 0 means, what is the meaning of omega equals 0? The frequency equals 0 means t equals infinity. Am I right? F equals 0 means 1 over t equals 0, hence t equals infinity. Am I right? T infinity means your voltage is a DC voltage. Right? T infinity means your voltage is a DC voltage. When you have a DC voltage across the capacitor, your steady state resistance or capacitive reactance, or I would say reactance, is infinity, and hence there will not be any current. Right? If omega approaches infinity, which means very high frequency, right? If omega approaches infinity, what will happen to Xc? What will happen to Xc?
0.
Yeah, Xc will become 0, right? So at high frequencies, your reactance will be 0, and hence it will be short circuited. Yes, it's correct, right? Someone of you have sent the answer in Zoom as well, right? So if your frequency is 0, the capacitor will be open circuited. If your frequency tends to infinity, your capacitor will be short circuited. Clear? Right. Now comes here this pi by 2. Pi by 2 means, right? So this is your sine theta and plus phi by 2, right? Your waveform will be added a phi by 2 here. Right? This will be 0 plus phi by 2 will be started from here, something like this. Right? This will be the waveform through the capacitor. Right? So if you have a capacitor, right? Apart from that capacitive reactance, you have another phi by 2 angle phase shift. Clear? Right. Now we'll move to the inductor. If you have any questions, you can ask me at the whenever you have, right? If you have any difficulties in asking the question, just send me a message in chat. Okay. Right. Yeah, the chat box is open, so you can just send the message to me. Yes. Okay. All done. I can see all of you along with the chat. Right. Now, go for the inductor. Inductor is just a coil, right? A coil, copper coil, right? Hope all of you know what is an inductor, right? This is E naught sine omega t. This is inductance L, right? With an inductance L. Right here, we can write the inductance equation, right? Where V equals L into d dt of current I, right? D dt of current I, which means the other way around of capacitor, right? The other way around of capacitor. So V equals L into d dt of I. Clear, right? So what is my VL? Equals E naught sine omega t. E naught sine omega t. Right. So look at here. You need to calculate I, right? Your question is I, but that is in terms of a differentials, right? So just integrate it both sides with respect to time t, right? With respect to time t. So I can write this one as L into di. Am I right? So this di will be there, dt will go to the other side. E naught is a constant, so I can write it as E naught into integration sine omega t into dt. Clear? Sine omega t into dt. Right. So what is integration di? Will be your I. Right, the current through this one I. So I can write I as equal to E naught divided by L into, what is integration sine omega t dt? What is integration of sine omega t dt? Integration of sine omega t dt? Minus cos omega t into omega. Am I right? Sorry, minus cos omega t divided by omega. Clear? Right? So I would say integration sine omega t dt. I can put the omega here, cos omega t, and I have a minus. Right? So I can write this one as minus E naught divided by L omega into, again, cos omega t. I can write it as, right? So there is a minus. So I can write minus cos omega t as sine 90 or 5/2 minus omega t, right? Sine 90 minus theta will be minus cos theta. So this minus becomes plus. So I can write my equation as E naught divided by L omega into sine, since it is 5/2, I can write it as omega t minus 5/2. Clear? Right. Now compare this one with your resistance equation here. Right? So I can simply say, just tell me whether you can see the letters or not, right? So this is your resistive equivalent, and here we have L omega, right? So I could say my reactance due to a capacitance, which is XL, equals L into omega, right? Since I have 1 over R, I am making it as 1 over omega here, but here both are in same, right? R and L omega. So I can directly write this as L omega, right? So when an inductor, right now, again, XL is a function of frequency. XL is a function of frequency. When omega equals 0, XL becomes 0. Am I right? XL becomes 0. So omega equals 0 means DC, this wire will be simply short circuited, right? And inductance will be short circuited when you connect it to a DC voltage, right? When omega tends to infinity, again XL will be also tends to infinity, right? At high frequencies, the resistance offered by the inductance will also be higher. Clear, right? So these things are really important. Now look at these three equations, right? Look at these three equations. Here you have R, there are no phase shift. Here you have, instead of R, you have 1 over omega c and 5/2 phase shift. Here you have L omega t, but a minus 5/2 phase shift, right? I would say a leading phase and a lagging phase, right? Phase difference between voltage and current will be leading, right, in an inductor, right? The current will be leading in a capacitor, and current will be lagging in an inductor, right? Please tell me again. What do I need to repeat? You're asking about this one, right? Just compare these two equations. Right here we have 1 over omega c. Right here, right? Can you see three equations? This one, right, and this one. Clear, right? So here we have R 1 over omega c, which is xc, L omega, which is xl. Right here we don't have any phase shift, right? Just omega t plus 0. Here plus 5 by 2. Here minus 5 by 2. Okay. So what I can do is I will put the recording, right? So if it is only the connection problem, you can go through it again, right? You can go through it again. I will post all the lecture notes because I have some data problem. Last month, I couldn't upload my videos from my home. So yeah, I can do it from the university too. I will upload all the lecture notes, right? All the lecture note recordings. Don't worry. Okay. Right. So what I can in summary, I would say current leads in a capacitor, current lags in an inductor. There are no phase shift in a resistor. Clear, right? So these are the summary of these three components when they are connected to a DC voltage. Right now, let's see how they are working. Right? Okay. Right. We'll go for the complex notation. Right? Complex number notation of inductance and reaction. Right? See here, instead of R, we have omega c, right? We have xc. I would say this as xc. But we have another 5 by 2 here. A 5 by 2 phase shift, right? So this is not enough, right? This variable is not enough. We also need another representative method to include the phase as well. That's why we are moving towards a complex numbers, right? A complex number you have studied already, right? So I would say x plus iy, right? So you all know that, right? Square root of -1, and right, let this be z, right? Mod of z equals square root of x squared plus y squared, and argument of z, or the phase angle of z, equals tan inverse of y by z. Am I right? Mod of z, argument of z, and where you have I. Why I have I here is, of course, if I have a 90-degree phase shift, right? If I represent that one in a complex coordinates, I would say this will be I. This will be real number, right? And this is complex. Right? I can represent my 90-degree phase shift plus I through this one, right? So this is, and then minus I through this one, right? Minus I through the negative axis, right? So I have like this, right? To represent that, I just add a J with the L, right? I can add a J. For example, XL, I can write it as J omega L, right? J and I both are equal, right? So I would say I omega L or J omega L, right? Both have same meanings, right? XC equals 1 over J omega C. What is 1 over J? What is 1 over J? Anyone? What is 1 over J? Or 1 over I? No. Work. In the class, message board. Okay, right? So what is 1 over j? See, what is j? J
Minus
equals
j.
yes, minus j, right? 1 over j equals minus j. I would write it as minus j by omega c, right? Which indicates, right? Minus j means, right? Here I have minus, and here I have plus. For L I have plus, C I have minus. So with this omega c, I am just adding this j to represent the phase angle, right? If it is j plus 90, if it is minus j, that will be minus 90. Okay, right? So that's all about it. You can use this notation to simply solve the problem. Right now, consider a combination of a resistance R and a C capacitor. Right now, I have connected this to a sine wave solution, right, which is E naught sine omega t, right? So the question is, right, I have a current I, right? I have a current I, right? The question is, what is the magnitude of current and the phase difference between the voltage and current, right? So this be E naught sine omega t. Right, so I can write this one as, right, so I can write my impedance, right? This is called as an impedance, as resistive impedance is simply R, right? XR will be R plus, what is the impedance offered by a capacitor? Will be 1 over j omega c, right? 1 over j omega c. Right, so now I can write this equation as R minus j by omega c, or R minus j into 1 over omega c. Am I right? R minus j into 1 over omega c. Now, what is my mode of z? What is my mode of z? Will be square root of R squared plus 1 over omega c whole square. Clear, right? So this will be your mode of z. And what will be your argument of z? What will be your argument of z? Tan inverse of, this will be your y, right? Y by x. Tan inverse of 1 over omega RC. Clear, right? So this will be my mode of z. This will be my argument of z. So I have my current, which is E naught sine omega t. This is my mode, right? Mode means, mode value means which I am using to divide this one. So my current, I can write I as E naught divided by mod of z into sine omega t plus argument of z. Right, so I can write this as E naught divided by R squared plus 1 over omega c whole square into square root dot sine omega t plus, yeah, let this be theta, right? This be theta. Clear, right? So this is how solving your simple circuits. Right, in this circuit, when your frequency increases, what will happen? When your frequency increases, what will happen? Yeah, j omega c will be decreasing and it will be approaching 0. Am I right? When omega increases, 1 over j omega c will be approaching 0. So at very high frequencies, I can neglect the effect of resistance. Right. When the omega reaches 0, then this will be open circuited. And of course, even if we have a resistance, the current will be 0 because that will be open circuited at this point. So there will be no current through the RC circuit. Clear? Right. Now we can go for an LCR circuit, right? LCR circuit. LCR circuit means I have a inductor, which is my L, and then a capacitor C, and then a resistance R. Right? This is connected to an AC signal. This is connected to an AC signal. Right. Now, okay, shall we write down the total impedance offered by this LCR circuit? Right, so I can write, yes, of course, when if it is that equals R will be R plus 1 over j omega C plus j omega L. Am I right? 1 over j omega C plus j omega L. I can write this one as a complex number now, right? So I can write it as R plus, this will be minus j by omega C, right? I can take j outside, omega L minus 1 over omega C. Am I right? Omega L minus 1 over omega C. Right. Look at here, the capacitance, right? The capacitive impedance is going to decrease with frequency, and inductive will be going to increase with frequency, right? So this here you have two variables which are at the expense of increasing capacitive reactance, the inductive reactance will be reduced. When it increases, this will be reducing. So there will be a nullifying point at the middle, right? For example, I would say, right, see here, this is an equation at omega equals omega naught at a certain frequency, right? I don't know what frequency it is. At omega equals omega naught, this whole imaginary part becomes 0. Am I right? So I would say, yeah, I would represent this, right, with capital Y. Right, at omega equals omega naught, I would say Y equals 0. So I can write it as omega naught L minus 1 over omega naught C equals 0. Right, so I can put the other side and I can bring it to the top, right? So I can make this one as, yeah, if this one is 0, I can make it something like this. Am I right? Since I have a minus, I can bring this one to the other side of the equal sign, and I can cross multiply this one, right? So I can write it as omega naught square equals 1 over LC. Right, hence omega naught equals square root of 1 over LC. Right, omega naught equals, right, when your frequency omega equals 1 over LC, right, square root of 1 over LC, your imaginary part becomes 0. Am I right? Your imaginary part becomes 0 and the total impedance is going to be only the resistor. Right? It is going to be only the resistor. Hence, if you draw the frequency versus magnitude current curve, right? I versus F curve, right? So that will be something like this, right? And then it will reach a maximum and then it will be reducing again, right? This maximum point, right? The current maximum can be achieved whenever your Z becomes minimum. Am I right? What will be Z minimum? Because R is not depends on your frequency, right? So it is not going to change at any case or at any amount of frequency. But omega L minus 1 over omega C can be equal when the frequency equal to 1 over LC, right? Square root of 1 over LC. That will be your omega naught, and this is called as resonance frequency. Right? Resonance frequency. Right. Now, how many of you are hearing FM radios? How many of you are here using FM radios in your house, in your home? Right. In FM radio, actually, we have a huge range of spectrum of electromagnetic waves, right? But when you tune a particular FM, for example, if it is 105.1 megahertz, right? For example, if it is 105.1 megahertz, right? Your radio have to choose only that frequency. And it should neglect all the other frequencies, right? So we can adjust that one based on these resonance. If you're 10, you have to design an LC circuit using this equation, right? If 1 over LC equals 105.1, then you will have I maximum at that frequency, and all the other frequencies will be eliminated from your circuit, right? So you will have only that particular frequency, and you can hear the data which is transmitted using the frequency. Clear, right? So this is what they are using in radios. Then you can tune it, right? You can change the values. You can tune the values. How can you tune the value in a radio? Yes, you are using a variable capacitor, right? By tuning it, you are changing the capacitance of a variable capacitor connected in the resonance circuit in your radio, right? If it is 1 over LC, while you are turning your LC, right, square root, right? While you are tuning the LC, you can adjust the frequency what you need at the output. Clear, right? So this is how your radio circuit works, right? Radio circuit works. Now, okay, we'll see these are LCR are connected in series. Series LCR circuit, and this is called as series resonance, right? Resonance in series LCR circuit. Right now, right, we'll consider a parallel LCR circuit, something like this. LCR, right? Okay, I'll leave this one for you for practice, right? For you for practice, right? You can upload this. I'll create an assignment in Google Classroom, right? So you can write down the equation. Why? Because 1 over Z, right? Because these are connected in parallel. So 1 over Z equals right? So XL, right? This should be XL, XC, and R, right? 1 over R plus 1 over XL plus 1 over XC, right? So 1 over Z equals 1 over R plus 1 over J omega L plus 1 over J omega C. I can write this one as 1 over R plus J into this will go on top, right? Omega L C will go on top, right? Omega C minus 1 over omega L, right? This will be 1 over Z. So what will be your Z? What will be your Z? Yeah, inversion of this one, right? You have to invert this one, right? And then you have to multiply by using complex conjugates to get a value there, right? To get a complex number and equate the imaginary part of that complex number to 0. So you will get the resonance frequency omega naught. Right, so hope all of you are in the Google Classroom. I will create an assignment on this one. What you have to do is you have to complete this one and you have to find out what omega naught for a parallel LCR circuit. Okay, right. Any questions? Any questions?
Excuse me, sir.
Yeah, tell me.
Can I have the passcode for the Google Classroom?
I think Ravirajan sir had all of you, right? I don't know. I didn't create it. Give me a second. And I'll send you the invitation. Think yeah, he had me as a teacher, so I was planning to use the same one, right? Same as his Google Classroom account. Give me a second. Yes, I think he posted his September 14th class. So okay, I'll send you the link. All of you are added there, right? 69 of you are there. If anybody missing there? Okay, I'll put it in the okay, I'll put it in the chat, right, for everyone. Use this link. I also add this one in the WhatsApp as well. Okay. Okay, I'll add the